I'm Bruce Bugbee, president of APOGEE Instruments, and I'm here today to record the keynote talk that I gave a few weeks ago at the LightSym Symposia in Seoul, Korea. This was the very opening talk of the conference, and it was a great honor to be asked to do this. What I chose to talk about is not the details of our photobiology research that my students have done, especially over the last 10 years, but as the opening talk to the symposia of research scientists, I wanted to talk more about the process of science and how we use our instruments and tools to create new knowledge. So these next few slides are what I showed there. My opening slide was this. This is a picture drawn by an artist here in Utah, James Christensen, of a home tinkerer taking his new spaceship out for a drive in the space. And I've just loved this picture. It's framed in my laboratory, but he's got all these gizmos that he rigged up. This is far from high tech. In fact, I think the title of this was low tech. But this is what we all do in our research laboratories: tinker with things, build gizmos, test hypotheses. They're much different than a commercial enterprise that might all be built out of stainless steel and something fancy. There's the name of the symposium, LightSym 2024. This drew several hundred research scientists really from all over the world. So it was truly a great honor for me to give the opening talk of this. And as part of that, it's light and photosynthesis and photons. So I want to start with a review of where we have come with creating light for ourselves over the past 150 years. This comes from a paper in the journal Nature, which I published with some colleagues, LEDs for Photons, Physiology, and Food. And in this review paper, we talked about the history of light. We started with kerosene lamps. What was the energy in the kerosene and how much light did we out? Now, this is light measured in lumens per watt of power going into this. 0.4. Now you can see the tremendous breakthrough when we got incandescent bulbs. Went from 0.4 to 15. It was an incredible advance. And in fact, that was a 40-fold increase of turning energy into light. Now, this is all for people, but plant research, as I'll show in a minute, has followed this. Then just after World War II, in about 1950, we got fluorescent lights. And that was another big advance from 15 to 80, but that was a 5-fold increase. But it was a huge advance for everybody to more light, less heat. Then in the 1970s, we got high-intensity discharge lighting. There's a high-pressure sodium bulb, 80 to 120. Another huge advance. Now we're only talking 1.5x. But each of these allowed us to do more plant research, mostly with higher intensities of light. We weren't doing so much back here with ratios of colors as just getting the intensity up. But we still used a lot of colored filters to create different ratios of colors. And some of my early papers right in here were using HID and metal halide lamps with filters to get different colors of light. And then, kaboom, we got LEDs. Roughly depending on when you say we started 10 or 20 years ago. And now, another huge breakthrough in terms of ratios of heat and light. This is for human lighting, lumens per watt. But if we do this in micromoles of photons per joule of energy, and this is the ratio for energy and photons out, here's the comparative numbers, and look at this, 0.005 to 4. This is almost a 1,000-fold increase in light. And even here, even if we start with incandescence, a tremendous breakthrough. So now we get all the colors, we get very efficient in lights, so we can have high intensity. This is why we're all assembled here for LightSym, to talk about our exciting work that we can now do with LEDs. This ratio, let me go back one. This is really light to heat. Lumens is light, watts is heat, micromoles of photons is photon flux density, and joules is energy. So this is the ratio of these two. So what is sunlight? It turns out sunlight has 2 micromoles of photosynthetic photons per joule of thermal energy. We don't think about that ratio much, but I'll show you. It's not difficult to calculate for sunlight. Now we have LEDs that are 3 and they even exceed 3 micromoles per joule. Just on this basis, it's staggering because look, we've caught up and passed sunlight with our human technology. It's just incredible that we've done that. And some people have said, yes, so now we don't need sunlight anymore. Electric lights are even better than sunlight. But look at this. This joule of energy right here, let me get that back, right here, and get my pen turned on. This joule of energy right here is electricity. We have to pay for that joule of energy. This joule is free from the sunlight. It comes with the sun. So we get 2 micromoles for free and we pay for these 3. So sunlight is still a tremendous source of light because it's free compared to electric lights. But it's still 3 to 2. Where do we get 2? This is a spectra of wavelength of sunlight and intensity. Here, it's a classic. Apogee has refrigerator magnets with this spectra on it. This part right here, we say visible, is really photosynthetic photon flux. And this red part out here is thermal. It doesn't drive photosynthesis. It drives evaporation of water. It drives transpiration, but it doesn't drive photosynthesis. So if you look at this is 2 and 3 based on this ratio of this. Now, if we include far red photons in this, that's this zone right here, 400 to 700 nanometers. This shifts this over slightly, so now a greater fraction of sunlight is photosynthetic radiation. And I'll come back to this in this talk a bit, but as most of you know, this is a huge part of the research of my students and I, of the value of these far red photons. If we include this number gets slightly bigger, 2.3 micromoles per joule for sunlight. But we're still not trying to catch up to electric lights. We're still trying to get favorable ratios of light to heat. And if we do that well, we can air condition greenhouses. Now that seems cost prohibitive now, but let me show you the innovations in glass that allows us to do that. This is, once again, here is our, let me get this in black right here. This is our PPFD. Same as visible light right here. Draw a line right there. This is the good part. We want a lot of this. This is standard glass that we've had for 100 years. If we put a coating on this, it slightly decreases visible, but it dramatically decreases the heat. And if we put more coating, even more and even more, so all of a sudden we have almost pure light and very little thermal, unusable thermal out here. When you use a low solar gain glass, we can air condition greenhouses. It's important to quantify this. That's why Apogee sells a flotilla of sensors to rigorously quantify these ratios. But this is a cutting edge of photobiology and food production in highly controlled environments, is to use the right kinds of solar glazing so we can close a greenhouse, not only reduce the air conditioning costs, but allow us to seal it and elevate CO2, take advantage of high CO2. That comes from innovations in glazing. Now let's go back to the history of photobiology to the 1950s. This is when we were working with fluorescent tubes, and at Caltech University in California, Fritz Wendt did his pioneering work. and he's a famous scientist credited with the discovery of auxin. Here's his work from a plant physiology textbook on auxin, of the hormone auxin. And he wrote this book, The Experimental Control of Plant Growth. It's a wonderful book about all these discoveries of photoperiod and temperature interactions. And this is in this famous Caltrek phytotron, where they could wheel carts from different temperatures of rooms and different lights of rooms, all done with fluorescent lights. Some of his famous quotes are he urged everybody to work in controlled environments, do more basic research, understand things at a very fundamental level, and now we have way better tools than he ever had to do this. He advocated for very simple experiments, don't do complex experiments, and he was very suspicious of studies that needed a lot of statistics, where we had a lot of treatments and a lot of statistics. He wanted fundamental data with more clear results. That continues to be very wise advice for all of us 50 years later, to do simple experiments with clear results where we associate mechanisms with experimental results. I want to build on this concept now in my next few slides. Another famous scientist, Ernest Rutherford, Nobel Prize in Chemistry, 1908. Here's Ernest Rutherford with his primitive tools of the time, working out breakthroughs in chemistry. What did he have to say about statistics? If your experiment needs statistics, you ought to have done a better experiment. That's still wise advice. Do simple experiments with clear results, not complex experiments that need a ton of statistics to interpret them. Not that statistics is a bad thing. We all use it. It's critical, but we shouldn't rely on the crutch of statistics to design our experiments. They should be clear, fundamental tests of hypotheses. Sometimes we design experiments that are more like a fishing trip than a real research. We're just going to do a lot of stuff and see what happens. Good luck getting your proposals funded if the reviewers think they might be a fishing trip. Serendipity plays a huge role in science. We still go for what we're looking for, but the public thinks the most exciting phrase in all of science is, eureka, I just discovered it. That's not how it works. The most exciting phrase is, that's funny. There's an outlier here. Who said that? Isaac Asimov, famous science fiction writer. And that's highlighted in this book, Serendipitous Discoveries in Plant Science. You can never plan for serendipity. You have to be doing good science, but you have to have a trained mind to understand when there's good data and when there's bad data. And we all need to train our minds to be looking for these unusual data when they arise. Another famous scientist, Louis Pasteur, 1800s, chance favors the prepared mind. This is one of his most famous quotes. I have just loved this my whole career, studying in graduate school to get my prepared mind for that chance moment. What that really means is when you have data like this, and now you say, here's my curve for the response. Let's get this in yellow. Here's my curve for the response. I don't like that data point. That's an outlier. I'm just going to take it out. How do you know that's an outlier? Just because you can draw a nice smooth curve for the rest of the data, we should be looking at outliers and understanding what caused them. That's why this quote is so famous. And by the way, when you read his original stuff, 1, 2, 3, 4, 5 words, how elegant is that? That's not what he originally said. It says, in the fields of observation, chance favors only the prepared mind. So subsequent editors said, we can do better than that. Let's take that out, take that out. We got his 5 words, but it was edited from his original quote. That speaks to the value of editing in our writing, too. Here's a famous saying. Everybody believes a measurement except the person who made it. Now, this is an amazing thing to say as an instrument company. We're all about making measurements, but some of those measurements are so hard to make, you got to be skeptical of your own data, even if other people believe it. No one believes a model except the person who made it. So people that make models say, yeah, I've modeled this, I know all about it. What this really means is we should be more skeptical of measurements and do more careful models. But more than anything, it's the combination of measurements and models that leads to knowledge. We need to go back and forth between these in all of our science. Too often we make too many measurements without the underlying principles, without connecting them to theory, and it leads to bad data. And if we do only models, we lead to crazy models not connected to reality. It's the back and forth interaction that helps us proceed in science. And I've used this analogy of a person going to the top of a house on 2 step ladders. One step ladder is measurements, one is theory or models, and you get to the top faster if you take 1 step on each ladder and you go back and forth and you get right up to the top of the house. You could get there by making only measurements, but pretty hard to jump on 1 step in a ladder or 1 step here. It's better to go back and forth. So as a sense of back and forth, I made this little diagram. Here's theory and knowledge far apart, back and forth, back and forth. We gain wisdom as we go. But what if we move those closer together? High frequency, back and forth, we make a lot faster knowledge. And then here we are in Korea. If we can conclude theory and measurement within the same person, that's really efficient for advancing science. So my point here is become excellent at making measurements, but become equally excellent at learning the theory and the underlying principles of this. Now let's shift for a few slides on photobiology. This is from a paper by Brodersen and Vogelmann many years ago. They did optics of light. This is a side view of a plant leaf. This is a pretty famous picture. Here's the top of the leaf. Let's see if I can get this in here. There we go. And here's the bottom of the leaf. Green light penetrates better than red and blue. We think these are so photosynthetic efficient, but they're absorbed in that very top layer. Green penetrates this. Green is an underappreciated value, and not just does it penetrate a leaf, but it penetrates the whole canopy to the next leaf below. This is the basis for a lot of our findings, just this simple concept of red, green, and blue. But now I would like to add another wavelength to this. We can't really call it a color. I've put far red in here. Now all of our data is clear that far red has photosynthetic value. I'm going to show you that we've shifted definitions of photosynthetic wavelengths for this, but far red is also very penetrating in plant canopies and in leaves. And sometimes we only study single leaves. We underappreciate the value of these colors in canopies. This concept of 1, 2, 3, and adding a 4th category has really helped advance our science in this. And look at the profound impact. Lettuce, more than any other crop, lettuce really responds to far red. Cell division, cell enlargement, we add a little bit of far red and we more than double growth of the lettuce. This is a combination of photosynthetic photons and cell expansion and cell division associated with far red. And we call this the shade response, but we can trick the plants to thinking they're in the shade when they're in the sunlight. It's just a powerful image of the importance of far red. This had led to a shift in how we define photosynthetic photon flux density. Here's 400 to 700, the conventional definition that we've used for half a century. Here's extended photosynthetic photon flux density with another 50 nanometers out here of photosynthetic photons. And it's this part right here that resulted in that lettuce plant enormous increase in growth. What we advocate is measure and report both of these in papers. We need to understand the growth per unit old definition, but also for the new definition, EPPFD. But now we're learning, when does this apply and when does it not? This is Paul Kasuma, got his PhD with me. He's at Wageningen now. This is the paper that resulted in this. These were studies with lettuce at 3 intensities, a very low intensity of 100 micromoles per meter squared per second, doubling to 200, and then doubling again to 500. Now, this is an excellent wavelength. And you can see we added far red, percent far red, we added up to 30%, and the lettuce responded. That's where that picture came from in the previous slide, right here. If we only gave them lower light, that line is flat. There was no benefit of far red if the light intensity was low. This is with what we call substitution. As we added far red photons, we took away traditional photons. So the EPPFD was exactly the same. And if they were in very low light, it was actually inhibitory. They needed those shorter wavelength photons. So what do we do when we do this? We normalize percent of control, and this is the data, normalized to 1 here. And now the trend becomes very clear. Far red was far more beneficial with a higher total background of photon flux than a lower background. This is going to be followed up by a lot of people, I'm sure, but it's a very fascinating interaction of far red photons and total amount of light, which again, we need to measure both. Spinach, you would think, responds like lettuce, but it's a different genus, it's a different species. All of our studies with spinach have shown it's much, much less sensitive to far red photons. This is a picture. Here's far red percentage, same as the other one. Instead of data points, it's a picture. This, and 100, 200, 500, the same study, far red minimally increased growth. Growth increases a lot with more intensity, but more far red, minimal effects. All of these pictures are similar here. So we have a lot to learn about interactions of far red with photon flux. These studies were done by Noah Langenfeld. In my laboratory, we're following up on these interactions with other species. Fascinating photobiology. Now we have a very powerful tool. We're going to hear numerous talks in this conference about all these principles applied to plants. I'm excited to be here. I'm excited to hear all these talks, and thanks for listening.